Chowdhury. I think that's a very lovely introduction for me. Thank you. And I'd just like to comment a bit on this fantastic technology we're using today, because although it's extremely effective and it makes a big impression on the bottom line of any company or business, what I miss from this is all the learning experience I get from being with all of you during the lunch times and the coffee breaks and all those opportunities we have to interact with each other and learn about your businesses and your challenges. So I do miss that quite a lot, but here we are, and this is very effective in its own way. And it did give me an opportunity to to listen to some of the other presentations that were going on earlier today. Obviously, functional coatings, this is about everyday work for us, and we enjoy this very much to listen to the presentations and learn from that. And I did listen to another session earlier, which was about innovation to
Hello.
there we go, that's better. And I think that the point about innovation to market is very relevant for this next session, because trying to get technologies that are new into our industries is a big challenge. And so some of this technology, we talk about it as innovation, but in fact, the actual chemistry has been around for quite a long time. It's just a question, how do we introduce this and get this accepted? So without further ado, I will click onto my presentation and bring it up full screen. And hopefully you can see it there. So I'm from Jotun, and I think most people are aware of who Jotun is. So I'm not going to spend any time getting onto that part of it. You can all make contact with us at another stage. But I would like to talk about these low molecular weight tank linings. And they are, the ones I'm going to talk about are Epoxy Novolac, but I'm going to touch on some of the other chemistries around this that has taken us to this point so far. Solvent-free tank linings have been around for a very long time. There's nothing really new in this. I think we can go back some 30 or 40 years. And there's a lot of drive towards using solvent-free tank linings these days, not least because of health and safety. For example, if you were to go to China, they're actually banned using tank linings which contain solvents, because the solvents, if you don't ventilate well, can build up in the bottom of those tanks. And should you have a spark, could create an explosion or at least a fire. And that's obviously not desirable in any way, shape or form. Another reason could be improved performance. And you'll see I've put a question mark beside that one, because what does improved performance mean? Just because it's solvent free, just because it's high technology, doesn't necessarily guarantee that you get improved performance. So I'm going to tackle that. And the reason I do that is because historically, the old-fashioned solvent-free epoxy tank linings have been highly viscous, difficult to spray. You maybe need to heat the pumps, you maybe need to heat the pipelines, and is therefore a challenge in real life, because no matter how clever we are in our laboratories, we need to ensure that we can use these products in real life, on site, in difficult conditions, or the conditions that are thrown at us at that time. It could be time, could be many different reasons for being challenged. And very often we've gone to two-component spray equipment. Now, two-component spray equipment has become much better the last 10 years, much better. But if you go back to when we were talking about these early solvent-free tank linings, that was a challenge. They would break down constantly. So where do we go to get a solvent-free coating that offers benefits, that is performing highly, and bring it into the practical real life? Well, that's where we talk about low molecular weight tank linings. Now, for a chemist, and any of you chemists sitting out there, you'll know exactly what I'm talking about with low molecular weight, but I will come to that chemistry in a moment. One of the things you need from a tank lining, you need good chemical resistance for the chemicals you're going to store in that tank. I mean, that sounds so logical, but it's not always the case. I have come across certain facilities where they have maybe 7 or 8 different chemicals to store. They only want one tank lining on all of those tanks, and they can't possibly resist everything that's going to go into them. So we need to think logically, what can be done by this tank lining? It should be easy to apply. And in our industry, I noticed the question a bit earlier, how do we apply these equipments? Well, in heavy industry, we use airless spray equipment and we need reasonable lengths of hoses. I'll come back to that in a moment in order to spray practically and well. And then, of course, with the health and safety, low VOC or zero VOC, and therefore a low risk of explosion. So that's fine. But the big issue is getting these products onto the steel in a good way. And that means you've got to think about what kind of pump you're going to use. You've got to think about what kinds of hoses you're going to use. I'm not going to go into too much detail of that because I want to talk about innovation. And the innovation starts with the smallest of the molecules that's important for us here, and that is the epoxide group. And this epoxide group is the clue to all epoxy technologies. But it's not quite that simple, because if it was, well, we wouldn't be sitting here today, would we? So here is a very good example. And it is, please take this with a pinch of salt, because this is the basics of the whole business here. And this is the different chemical groups that add a benefit to the product. Now, this is the basic resin. Of course, you put in hardeners, you put in additives, you put in extenders, lots of things that change the performance of a coating. However, it's good to go back one step and see what's in here. So if you look here at the main functional group here is the epoxide ring, the epoxy group. What that's doing is interlinking and interacting with the hardeners that you put into the product. And that gives you good cross-linking, which gives you good chemical resistance to some extent and good hardness properties. If you then move further on, you've got the ether linkage, and that ether linkage gives you the corrosion protection we will need, because in most cases, tank linings are used not to protect the steel from the chemical that's in the tank, but when those tanks are not full, humidity causing corrosion on those tanks. That's what it basically comes in. There are exceptions with acids and so on and so forth. Now, that ether linkage also gives you mechanical properties, which you're going to need, because, for example, if it's a floating roof of a crude oil tank, moving up and down in that tank will abrade away the coating. Moving on, we've got a hydroxyl group that aids adhesion. You heard a previous presentation about adhesion. This is one of those characteristics that you need in a coating. If it doesn't adhere, you have a problem, right? Especially in the tank lining, because your tank lining, a little bit like the CUI we were talking about earlier, very few chances to come back and actually do something with it. You know, if it fails, if it falls off the tank, you have a major problem, both in your process operations, but also from a claim point of view and challenges with the job that was done. But we're talking tank lining, and tank lining is about chemical resistance. You need to be able to resist and stay hard when you put those chemicals into that tank. And that's where our good old friend, the benzene ring, comes in. And I say good old friend because anybody who's worked with chemistry will know that the chicken wire effect that you get from the benzene rings is a very important molecule for bonding everything together and giving you good chemical resistance. So there's two things I want you to think about here. That's the benzene ring for chemical resistance, and that's the epoxide, which gives you the cross-linking and the good approach. So what does that mean? Well, you have your different epoxy technologies, and we'll use the terminology that's out there in the market. Bisphenol A, that's your good old-fashioned basic pure epoxy. And what you'll see here is that there's an N here. N can be many, and this is where we're getting to the clue of the technology. How many shall that be? Now, traditionally with bisphenol A, this is a very long molecule with the epoxide group there and there on the other end, so on both ends. And these grab they grab the hardness, and it's very long and very flexible. Flexibility can be extremely useful when you have a paint because the tanks are moving, things are moving. The next technology that came along is something we call bisphenol F. You will commonly know it in general industry as the phenolic epoxy. And the phenolic epoxy, do you remember my benzene rings, the two of them in the middle here, and then you've got your epoxy groups on the edge here. So much tighter, less flexible, but increased chemical resistance and increased hardness from the general epoxy system. Moving round, we come to the novolac. Now, novolac is like calling a vacuum cleaner a Hoover or something like that. It's not a proper chemistry term because, in fact, it is in fact a phenolic type technology. However, what makes us use the term novolac is because you have a one-to-one ratio between your benzene ring and your epoxide group. And that, you can imagine, gives you tremendous chemical resistance from the benzene ring and cross-linking from the epoxide. There's one other thing that you may or may not notice, but certainly chemists in the audience will notice. There's a single bond here bonding all of these different groups together. There's carbon in the middle there, and they can spin on that single bond. On a double bond, they can't spin. Double bonds are these things you see on the benzene rings, but that's a that's a special case. But on the single bond, it can spin. So if you imagine on this novolac epoxy system, what we've actually got here is lots of spinning and therefore three-dimensional cross-linking. So when you put your hardener into the system, you're actually cross-linking in a three-dimensional form. So the whole paint film, not just layer by layer, the whole paint film is strongly cross-linked, forming a kind of tight mesh that slows down the chemicals from coming into the coating. We must also be aware that it will slow down them from coming out of the coating as well. So if one is to have many different types of chemicals in a tank, it will slow it down from coming out. Now here we look at the N again, and the N meaning many. How many? So when we were working with the original types of epoxy coatings and those solvent-free epoxy coatings that we looked at the beginning, they were more or less based on bisphenol A, and this N was very, very long. This is why you had high viscosity, and you needed, traditionally you would add solvent to make that work, but when you take that out, then you start to have problems. So what you do is you add into the system so-called reactive diluents. Now the problem with reactive diluents is they don't necessarily react 100%, meaning that over time they can leach out. At high temperatures, they can actually evaporate, because this diluent term actually has some criteria to it, meaning that when you go over a certain temperature, it will indeed evaporate away from the system, but it will happen very slowly, and it is still solventless, solvent-free. But the problem is its lifetime will reduce with chemicals over time. So you have to be careful with that. So the answer to that is make sure that N is not too big. And I'm not going to go into the details of what is big and what is small, because that's not important today. Because what's important is how you build this technology together with the other components in order to give you those benefits you're looking at and looking for. So what does low viscosity mean? You've got small n, so small molecules with therefore low viscosity. And that low viscosity, if we look at this picture here, gives you some certain advantages. So when you spray, and we talked about pot life, the pot life we were talking about earlier of how many minutes do you need to spray a can of paint. Well, you'll normally spray a tank lining. You won't normally brush it because it gives you a much better, more even finish. And you can normally take 20 litres and spray that in about 10 minutes if your applicators are good, which means that you can manage most types of solvent-free coatings, because if you look at the red bar here, you've got, I mean, sprayabilities up to about 2.5, 3,000 centipoise. That's centipoise on this side of the graph. So we're up here below 4,000. You can more or less spray it with good equipment and shorter hoses. So 10 minutes should be enough, you think. But for a tank lining to operate really well, you should actually give it a few minutes of induction time. Induction time is both components mixed together, and you wait a while for the chemical reactions to start going ahead. This gives you a better, more cohesive coating at the end of the day. But if you wait 10 minutes, for example, which is what we would ideally recommend, then you've only got 10 more minutes to spray it. And what happens then if you have a delay? Maybe you're climbing up some scaffolding to get to the higher parts of the tank, and you start to run out of pot life and it becomes more difficult to spray, and you need shorter hoses to get it onto the steel. That's a challenge. So by going to low molecular weight epoxies, what we do is we actually have, even when they start to harden, much longer time. And you see, to get up to 3,000 centipoise is about 50 minutes. And you can still, at 3,000 centipoise, use quite long hoses, meaning your pump equipment can stay where it is. This pump equipment is not something you put on your back. It's heavy. It needs to be moved by forklift trucks. So therefore, it's very important to manage that in a good way and have long hoses so you can access all parts of the tank. So what you see here is if you've got really good equipment and shorter hoses, you could even work up to 60, 70 minutes. But generally speaking, that's not necessary. So 30 to 40 minutes of sprayability with low molecular weight epoxies. Useful. We also then have to look at overcoatability. In a perfect world, you'll always do 2 coats of paint in a tank lining. And the reason for doing that, it's a human application process. So when you spray the first coat, you're likely to have variations in thickness around and about. You might have holidays, which was mentioned earlier. You test for holidays. If you do it in a single coat, it's quite likely you'll have so many holidays in that coating, so many gaps in that coating, that you're going to need to touch up almost 100% of the tank. Well, then it's better to actually say, let's plan and program for a 2-coat process, meaning that you average out the thickness and you remove the risk of having holidays in your coating. So if you're going to do a 2-coating process, how long do you have to do your second coat of paint? These could be big, big tanks, maybe 100 meters, 60 meters in diameter. So if we look here, traditional solvent-free coatings, they build up hardness. Now, 100 here in the hardness scale is glass. So it gives you an idea of how hard that is. And we all know if you paint glass, many of them, you can just peel them back off again. So that means you have a risk for adhesion. And for some reason, when we test it, we see that hardness goes very high up, then it slightly drops again. I've asked lots of chemists about this. None of us know why that happens in this case, but it did. That's a test result. But if you take the low molecular weight solvent-frees, they start with a much lower hardness. Now, it could be slightly negative if you had to handle these structures early. But after just 1, 2, 3 days, it starts to get up to hardness. You have a full week. 23 degrees centigrade, by the way. You have a much higher temperature in general in India. So of course, your hardness development will be much faster. But what we see is that even at 23 degrees, you're not reaching glass hardness for 7 days. And then it's going up to, over the course of 1 month, up to the same sort of hardness that you would have had with the standard solvent-free. What's interesting here is that you have that 7-day window, maybe that window at 35, 40 degrees centigrade, which is easy to get on the side of a tank in India. Then you might want to recoat it in 24, 48 hours, but that's doable. But if you look at the hardness here of the traditional solvent-free, far too quickly, meaning you probably have to do a 1-coat operation, or you might have to sand in between to get a physical adhesion and not rely on chemical adhesion between the coats. And that's not, obviously, that's not what you want. That's not at all ideal. So by going to low molecular weight, we've slowed down the whole curing process, which sounds weird because very often we want a fast curing process. But I do remember in the previous presentation, there was discussion about pot life, and that pot life and the way it reaches hardness is quite important. You have time to work with the coatings. So extremely useful. Yet given the time, you reach your hardness you want to resist the abrasion from, say, a floating roof. Now, what does that mean in practice for you? When you've developed this paint, it's going to be used. Why are we doing it? What does it mean? Well, we want to try to replicate solvent-frees to the traditional solvent-containing. Lower film thickness has some advantages, especially if you want it to dry out and cure and you want to reduce cracking. If you have very high film builds, we can often see as the tanks move with temperature and being filled and emptied, they will move, and very high film thickness could give you cracking risk. So keeping that thickness down is vital, to be honest with you. So what we find is the 2 by 200 microns dry film thickness is the ideal thickness. Also, by the way, when you use solvent-free, no need for fancy calculation. 200 microns wet is the same as 200 microns dry. Well, of course, that's a great advantage when you're working with applicators. They don't have to worry about that difference. So no fancy calculations. You apply 2 coats of paint, you get full integrity with about 400 microns. Now you could creep it down to 150 microns, but to be honest with you, calculate for 200 microns. But you can allow it to be 150 per coat, but calculate the usage at 200 microns, because real life is real life. Guys are working in difficult conditions with masks on, with gloves on, spraying with an airless spray. So be a little practical when you think about it. I already mentioned why not 2-coat system, but there's one added benefit here. When you do a one coat system, you would need to do spark testing, and I mean need to. It's probably in the spec anyway, so you're probably going to do it regardless. But when you do a spark test, you need a certain amount of cure in the system before you do that spark test. So if you're going to do it after a one coat system, you're going to have to wait for that to be cured. It takes longer for a one coat system to be hard enough for spark testing than a low DFT, meaning that you have to wait. Then you do your spark testing. Can you imagine going over a whole tank with a spark tester and then marking up everywhere that needs repainting and then going back and having to do it, ending up in effectively a two coat system because the spec says 1/300. So every holiday needs 300 microns applied. So you're doubling the amount of paint, being a risk for cracking, and you're creating extreme amount of work over a longer period of time than you would have done just to do a two coat system. And by the way, with the low molecular weight epoxies, you can do the spark testing after about 24 hours. So it's next day, effectively next day. What this gives you with the low molecular weight is also, it gives you a very smooth and clean surface because it's low viscosity, so it flows out very well and gives you a good result. So in practice, for all you practical guys who are doing real life out there, you can go for a large pump, a 60-to-1 King Graco type of pumps. You can go to 30 to 60 meter lengths of hoses. Makes life a lot easier. Keep the pump where it is, spray the tank. Filters don't need to be removed. We often recommend because some of the pumps have been well used, so they're a little bit not as clean as we'd like, not laboratory test conditions. So remove them anyway, but you don't have to if you have brand new equipment. We do like to see steel temperatures up to about 30 degrees centigrade, but can go lower, can go higher, but then take great care looking at technical data sheets, make sure you plan it and utilize the manufacturer of the paint. Ask those questions, make sure you have a plan for doing the coating job. Now, I've talked a lot of great things about the products. There is one caveat to the whole thing, and that is take care to use personal protection equipment. Now, I would say this for any paint product in the industrial environment. Use proper personal protection equipment. And that's during the mixing as well as the spraying. Now, with low molecular weight, what that means is that your sensitivity to it will be slightly increased. So if you are exposed a lot to it on your skin, in your face, then you could end up with getting some allergic reactions. And nobody wants that because that would be bad for the sprayer. So it's very important that also during mixing, because once you've mixed it, it starts to chemically react and it becomes a larger molecule and less sensitizing to the skin. So bear that in mind and take care of that part of it. Use PPE like you should, especially the mixers, because they're often forgotten. I've seen too many standing in shorts and t-shirt mixing. And what can you store in it? I mean, it's a good question, logical question. Obviously, crude oil all the way up to 140 degrees centigrade. Is that necessary? No, probably not. But that ability is there. You might be coating not just a storage tank, you might be coating a process vessel that needs to tolerate these temperatures. And the rest here, we have clean petroleum products, we have other chemicals, but main thing here, whoever is the supplier of that coating, whether it be us or someone else, always check the resistance list from that supplier. Make sure it truly is resistant in black and white, legally, and not just something a paint salesman is telling you for whatever reason. I mean, I'm not saying that we're not to be trusted, but let's be honest, when it's in black and white, when it's properly done in official documentation, you can't get better than that. So that's what I'm saying to you. So just in summary, this low molecular weight, 100% solids, novolac phenolic epoxies, they're great because they're better for health and safety in terms of VOC and explosion and fire risk. If you use proper PPE, they're very safe to use. Application with standard airless spray with long hoses, resistant to lots of different products like many epoxy linings should be. Crude oil up to 140, so that's great. And you have flexibility in your application process. So this adds value. Shouldn't get shrinkage, although the chemical reaction will give you ever so slight shrinkage, and no solvent entrapment, which sometimes occurs with a two-coat product. So short presentation, very quick. I hope it was useful for you. And I'd like to say thank you.